Hello, my name is Josh Wheeler. In this video, I'll be explaining a derivation of a force balance of equation dealing with some differential volume, explaining density of an ideal gas, and then also working with a force balance equation. So let's go ahead and get started. So let's go ahead and give our names. This equation, we're going to have a container. And in this container, we're going to have 1 mole of gas. This fluid inside this container is going to have 1 mole. So it's basically, you'll notice in my equations when I'm writing things out, I really won't write it down A and N because it's equal to 1. So you're multiplying by 1. So it really doesn't need to be there. So just notice that the number of moles is still there, but we're not going to write it down because it's multiplying by 1 in the ideal gas equations, you could say. So N is equal to a 1. We'll know that. So let's write down our container. So our container, I'll get 2 views of it. So our container right here is going to have, we'll write this up here too, a cross-sectional area up top represented by A. You can see this. So we have a cross-sectional area on top of this container. And with it, let's say we have a fluid inside at some level. Level Z, you could say. So this is at level Z. And it represents height in this. So you could say that as the level of Z increases here, it's going up positive. So as it goes up, it's increasing. So going up is a positive increase in Z. Okay. And we could also say that an increase, so if we added to this by some level, this is represented by a change in Z, or some small change in Z. So we could represent this level as differential of Z. Differential means a small amount. So a small change in the Z amount going from the original state to a higher state. And let's say we have some pressures on this. So we have a force acting from the bottom at level Z. So it's positive because it's going up. It depends on direction here in this case. So force Z is acting up in a positive direction. We have a negative force acting at the level of our original Z value. So pressure at Z plus the small change in Z. This is represented as Z plus dZ. And this is negative since it's going down. We already dictated that the positive Z-axis right here is going up, if you can see this. Okay. So now, we can also say that, okay, this fluid has a mass, and it is also being affected by the gravity. So there's a gravitational constant, so it has a weight, you could say. And it is acting down because it's negative. So there's a negative force of the weight. So it's mass times gravitational constant in this case. We don't have a mass in this case. We're just going to derive the equation. So there are no numbers. We're just working with variables in this time. Okay, so I believe that we have everything we need at this time. So we can go ahead and derive this equation. So let's set up a force balance equation. So in this, let's say we have our forces. In this case, we have the positive Z. Now notice that these forces are going to be multiplied by the cross-sectional area. Since in this case, I dictated above that our container is a rectangular prism. But I mean, you could use this equation for, oil drums, cylinders, certain different kinds of containers. So you could change the equation that you're going to use for the area to solve it out. Or you could have different areas in here. But in this case, I'm just going to use this cross-sectional area. Again, we're not working with numbers, it's just symbols, but I'm saying this can change depending on the shape of your container. So we're going to be multiplying our forces that we're going to have, either positive or negative, multiplied by the cross-sectional area, except for the mass and the gravitational constant, or the weight. We're not multiplying by an area there. So we're going to have our positive force, or P, our force at Z level, multiplied by our cross-sectional area, so A, minus our negative force at position acting down, position Z, differential change in Z, so adding them together at this level. So we're going to have Z differential change in Z multiplied by the cross-sectional area, and we're going to have the negative force of the weight acting on it at right here. So mass times gravitational constant is equal to 0. This is our force balance. Okay. So now, let's say that we want to start moving these around and start substituting in. So we can move our, let's move our mass and our gravitational constant, or weight, over to the other side. And we can also factor out a negative A in this case. So let's do that. So we're going to take and factor out, so negative A times our, let's see, we can change things around here. So let's do our force at position Z dz minus our force at position Z. Okay? So now, let's go ahead and move our mass and gravitation, our weight, to the other side. Okay, and we can actually substitute our mass out for density in this case. So we know that mass is equal to density times volume. All right, so we could say that we can actually substitute this in. And we know our volume, in this case, volume is equal to the area times some differential change in Z. So our area here moved up and down by the pressure. This small change, whatever it's moved, whether it's moved up and down, either a decrease in or an increase in volume, is represented by dz, or a small change in the elevation. So we can move this in here and actually erase this and say that instead of our mass times gravitational constant, we can say that we have a density times our, and we're also going to move, we'll go ahead and do this now. We'll divide by -1 and get rid of this negative on this side and bring it over here. So it makes it cleaner on this left side. We have a negative density times an area times a small change in our Z elevation multiplied by the gravitational constant. Okay? And you'll notice right here we have two areas on both sides, so we can actually cancel these out. And we'll also divide by our small change in Z on the right side and bring it to this side. So let's go ahead and do that. Let's do this real quick. And let's see. Let's take out our area and our dz and move to the other side, our differential change in the height. And what we're left with is our negative density times the gravitational constant is equal to the two pressures divided by small change in our Z. So now we can actually start simplifying this more and say that what we're left here, so we have a force at the top, in this case our force at position Z plus differential change in Z, subtracting our pressure at the bottom. So what this means is whatever we're subtracting this pressure, subtracting the bottom pressure, what's going to leave us with is the change in the pressure. So we can separate this and say a small change in our pressure is brought about by a small change in our z elevation. Okay? Let's do this. Like I said before, this is saying if we take our pressure up here, subtracting our pressure down here, we're trying to find the pressure and the change in here. So we can say that a small change in pressure, differential change, is brought about by a small change in our z elevation. And we can set this equal to, now we can actually start substituting our density here in terms of an ideal gas. So we know that density is equal to mass over volume. And we can also, this is where our n would be brought in here. But since n is 1, like I said before, we're not going to write it in here. It would be right about here. So we can actually start thinking about this in terms of an ideal gas. So let's say that this is really, let's take our m out for a second. So 1 over v, in this case n over v, let's take our mass out for a second. For an ideal gas is PV equals nRT. So if we substitute this around, we want n over v in this case, so we bring the v over here and divide by RT, so n over v is equal to our pressure over our R, which we know, times our temperature. So we can actually substitute this in and say that our density is equal to, since n is 1, we can take it out, and say that, let's see, we can say that our pressure times our mass, which we have, over top of our R times our temperature, and we can take this and substitute it in to our equation before. So this is where density was. So we have our G, which we're going to keep here, our gravitational constant, and these are negative. And we can substitute our pressure from our density is now in terms of an ideal gas. So we can take and substitute this in and say that our pressure times our mass, which we know, divided by R times T. And there you go. So now we've derived our equation down to where we represented our density in terms of an ideal gas. We use the force balance equation, and yes, we've derived an energy balance equation, and we've done it. And here's our answer. All right. Thank you for watching this video, and have a great day.